Polynomial rings in one variable over a field are an example of a type of ring that we're going to call principal ideal domains. As the name suggests, in a principal ideal domain, every ideal is a principal ideal, meaning that every ideal can be generated by at most one element. It turns out that principal ideal domains are very well structured, and we can understand the factorization of elements very well, and this factorization is guaranteed to be unique in a convenient way. We're going to get more into the factorization ideas later. For the moment, we're going to talk about principal ideal domains and some of their basic properties, and in particular, we're going to show that polynomial rings over a field in one variable are these kinds of rings. So we'll start with definition 119. A ring R is a principal ideal domain which we will usually abbreviate PID if every ideal of R is principal. That is, every ideal of R, I, can be written as I is the ideal generated by A, which in turn is equal to the set of all multiples of A by elements of R for some element A in the ring. Principal ideals are very nice because all the elements of the ideal are just multiples of some given element, some given multiple. Some given element of R, and everything is a multiple of that. So we've got some examples and some non-examples. So for example, the ring Z is a PID since every ideal is of the form NZ, which is the ideal generated by the number n for some integer n. For a non-example, we can look at the ring Z adjoin X, a polynomial ring over the integers in one variable. This is not a PID since the ideal generated by 2 and the variable X is not principal. Showing that this ideal cannot be generated by a single element, that is, this ideal is not principal, is a fairly straightforward exercise. So now we get to the theorem that really was sort of the motivation for defining this kind of ideal in the first place, this type of ring in the first place. Theorem 120. If capital F is a field, then the polynomial ring in one variable over X is a principal ideal domain. It's important to note that if we have a polynomial ring over a field in more than one variable, that is, if you were considering polynomials in, say, X and Y and Z, that's still a ring, and a lot of the results that we proved about polynomial rings in one variable will hold in multiple variables, but this result definitely won't. Polynomial rings in 2 or more variables are not PIDs. So let's see how this goes. So first of all, we'll let F be a field, any field. Now, notice that by theorem, by Theorem 91, f is a domain. So that means that f adjoin x is a domain. So in order to be a principal ideal domain, you have to be a domain first. I should have mentioned that in the definition, even though it's part of the name. So this is the first step. We have that f adjoin x is a domain. Now we need to show that any ideal can be generated by just a single element. And the difficulty at first glance with doing this is that if we go ahead and let I, subset of f of x, be an ideal, we don't know at this point anything about I except that it contains a bunch of polynomials in f adjoin x. And so if we want to try to show that it's generated by a single element, we need to demonstrate how we can actually come up with that element. And in this case, we're going to use a technique that we'll use a few different times as we're talking about polynomials and later on factorization and divisibility and things like this. So we've got this ideal I, and it contains a lot of different polynomials. In fact, it's going to contain infinitely many different polynomials. However, most of those polynomials are going to be a very high degree, because if you multiply two polynomials with degree, their degree can only go up or stay the same. They're never going to go down. So what this means is that if I look at the set of all possible degrees of elements of the ideal I, that's a subset of the natural numbers. And in particular, by the well-ordering principle, it has some minimum element. So, first of all, we need to get rid of the trivial case. If I is the ideal generated by 0, then clearly I is principal. So we may assume that I contains non-zero elements. So now let's let G in I be an element of minimal degree. Like I said, if you look at the set of all degrees of elements of I, that's a non-empty subset of the natural numbers. Therefore, it has a minimum element by the well-ordering principle, and or by the well-orderedness of the natural numbers, rather. We claim that I is in fact generated by this element G. If you take any element in I of minimum degree, then that is by itself a generator of the ideal I. Now clearly, since G belongs to I, we have that the smallest ideal containing G has to be contained in I, because I is itself an ideal containing G. So we need to prove the other direction. We need to prove that given any element of I, that element is in the ideal generated by G, which remember consists of all of the multiples of G. So now we can let f in I be any element by the division algorithm. Because we're working in a polynomial ring over a field, there exist Q and R in the polynomial ring f adjoin x with f equal QG plus R and R equals 0, or the degree of R is less than the degree of G. So if we rearrange this, means that R is equal to F minus QG. But by our hypothesis, f belongs to I. Also, g belongs to I by hypothesis, and so any multiple belongs to I. Because I is closed under subtraction, this means that R belongs to I. Now, if R is not equal to 0, then R would belong to I, and the degree of R would be less than the degree of G. But this is a contradiction. This is a contradiction because G was specifically chosen to be the element of I, or an element of I, of minimal degree. That is, there can't be anything else in I with smaller degree than G. So that means that we get a contradiction, we go back, and so that means that our assumption here that R is not equal to 0 can't possibly be the case. It can't possibly be the case that R is not 0. And therefore, R equals 0. So in particular, this means F is equal to Q times G, but Q times G is a multiple of G and therefore belongs to the ideal generated by G. So, since this holds for any element of I, this means that I is a subset of the ideal generated by G, and because we already had the other inclusion earlier, we have that I is generated by G. So this means that I is principal. So this means that F adjoin X is a principal ideal domain. In particular, this proof, the proof of this theorem 120 is very nice because it doesn't just tell us that any ideal in a polynomial ring over a field is principal, it also tells us how to find a generator of it. We simply need to take any element of the ideal that is of minimal degree, such that there's nothing smaller, nothing of smaller degree in the ideal. We can apply this technique to a specific example or a given example in a polynomial ring over a field in order to determine a generator of it. So, for instance, let's let the ring R be the polynomial ring in one variable x over the real numbers. The real numbers is a field, and so the previous theorem will apply. And so let's let I be the ideal generated by the polynomials 6x cubed minus 5x squared plus 2, and then 2x squared plus x. Now this is an ideal, and it's being presented to us generated by two elements. Now by Theorem 120, since I is an ideal inside a polynomial ring over a field, I has to be generated by some single polynomial g for some g in the ring R. Now, to determine this, we can use the division algorithm, and specifically we can use long division of polynomials repeatedly, if necessary, to figure out the element of I that generates it, or an element of I that generates it. So, for instance, by the division algorithm, we have that 6x cubed minus 5x squared plus 2 is equal to some polynomial q times 2x squared plus x plus some polynomial r. Now, in order to determine this q and this r, we can use the long division of polynomials algorithm. So dividing these two polynomials, we compare leading terms. We take the quotient of the leading term of the polynomial inside with the polynomial outside, and we see that that quotient is 3x. So we take 3x, multiply it by 2x squared plus x, and we get 6x squared plus 6x cubed rather, plus 3x squared. Subtract it, and we get negative 5 minus 3x squared is negative 8x squared plus 0x plus 2. And we get minus 4. Now minus 4 times 2x squared gives negative 8x squared. Minus 4 times x is minus 4x. And when we subtract this, we get 0, 4x plus 2. So when we do this, then the top part up here is q, our quotient. The bottom part down here is r, our remainder. You'll notice that the degree of r is less than the degree of the polynomial 2x squared plus 2. So we get that 6x cubed minus 5x squared plus 2 is equal to 3x minus 4 times 2x squared plus x. Sorry, one sec, let me move this over. Plus 4x plus 2. Now, note that just like in the proof of the theorem, 6x cubed minus 5x squared plus 2 is contained in the ideal I, because it's one of the generators. Similarly, 2x squared plus x is contained in the ideal I, and therefore any multiple of it is contained in the ideal I. And therefore, we have that 4x plus 2 the remainder is contained in I. As a more general principle, if you apply the division algorithm with any two elements of an ideal, the remainder has to also be in that ideal, just because the ideal is closed under multiplication by elements of the ring and closed under subtraction. So this means that 4x plus 2 is contained in the ideal I. So then we can say, right, well, maybe I is generated by 4x plus 2. So now we can use the division algorithm again on 2x squared plus x, one of the original elements of our ring, and 4x plus 2. When we do that, we get 2x squared plus x is equal to, turns out, well, we get 1/2 x times 4x plus 2 plus 0. So in particular, this means that 2x squared plus x is a multiple of 4x plus 2. In particular, it means that 2x squared plus x is contained in the ideal generated by 4x plus 2. Now, we also have that 6x squared minus 5x squared plus 2. If we apply the division algorithm with the other generator of the ideal and 4x plus 2, we get that this is equal to 3/2 x squared minus 2x plus 1 times 4x plus 2, which means that 6x squared minus 5x squared, 6x cubed minus 5x squared plus 2 is a multiple of 4x plus 2, and so it also belongs to the ideal 4x plus 2. So what we have is that the ideal I, which is generated by these two polynomials, is definitely a subset of the ideal generated by 4x plus 2, but because 4x plus 2 was also a subset of of I, the ideal I, we have then that I is generated by the polynomial 4x plus 2. Now, the actual polynomial that we write the ideal I as being generated by is not unique. So, for instance, because 2 is invertible in the ring R, we could multiply everything by a half without changing the ideal. So the ideal generated by 4x plus 2 is the same as the ideal generated by 2x plus 1. We can multiply it by the unit -1 and get -2x minus 1. Multiplying the generator of a principal ideal by a unit does not change the ideal. And so any one of these representations of I is perfectly reasonable as a description of it. Now, one of the reasons why we care about polynomial rings so much is because basically every ring that we encounter in every commutative ring anyway that we encounter in algebra can be thought of as a factor ring of a polynomial ring. Now, usually you have to use a polynomial ring in multiple variables to do this, but for simpler rings, we can do it with just a polynomial ring over one variable. So let's see that the complex number C is isomorphic as rings, and therefore as fields, to a factor ring of R adjoint X. We're going to use the first isomorphism theorem here, which means the first thing we're going to do is we're going to build a surjective homomorphism from R adjoint X to C, and then we're going to compute what the kernel of that is so that we can exhibit an isomorphism by the first isomorphism theorem. So let's let phi from the real numbers adjoin variable x to C be given by phi of a polynomial f, which belongs to R adjoin x, equal to f evaluated at I. So we're taking a polynomial and replacing all of its variables, indeterminates rather, I should say, not variables, with the number I from the complex numbers. Simplifying everything down, of course. And so this is the evaluation at I map. Phi is a ring homomorphism and it's surjective. The element a plus bi in C, any element a plus bi belonging to the complex numbers, is equal to phi of a plus b x. So now this means that as rings, the complex numbers is isomorphic to a polynomial ring in one variable over the real numbers modded by the kernel of phi. Let's see if we can determine what the kernel of phi is so that we can describe this isomorphism, describe C using a more precise ring over here. So let's note, first of all, that the polynomial x squared plus 1 is in the kernel of phi. And we can see that just by noting that phi of x squared plus 1 is equal to, by definition, what we get when we replace all of the indeterminates in this polynomial with I. So it's I squared plus 1, but I squared is -1, so we get -1 plus 1 is 0. So we have that x squared plus 1 is in the kernel of phi. We're going to claim that x squared plus 1 is a generator of the kernel of phi. We know the kernel of phi is an ideal, and therefore we know it's a principal ideal because the ring R adjoin X is a principal ideal domain. We're going to claim that x squared plus 1 is not only in the kernel, but it's a generator of it. By the proof of Theorem 120, we can do that by showing that x squared plus 1 is an element of minimal degree inside the kernel of phi. So let's show that there's nothing inside the kernel of phi that's of lower degree. So x squared plus 1 is degree 2. Let's show there's nothing in the kernel that has degree 0 or 1. So let's let a plus bx belong to the kernel of phi, degree 0 or 1 polynomial, depending on whether b is 0 or non-zero. So then we have that 0 is equal to phi of a plus bx, because that's what it means to be in the kernel of phi, which is, by definition, a plus bi. But a complex number is 0 if and only if its real and imaginary parts are 0. So that means that if a plus bx belongs to the kernel of phi, then a equals 0 and b equals 0. So a plus bx is in fact just the 0 element. So in particular, this means that no degree 0 or 1 element is in the kernel of phi. So this means that x squared plus 1 is an element of the kernel of phi of minimal degree, and so this means that the kernel of phi is equal to the ideal generated by x squared plus 1. Hence, we can describe the complex number C as a quotient ring of a factor ring rather, of the polynomials in one variable over R, modded out by this single principal ideal x squared plus 1. So, from an algebraic point of view, the complex numbers are just like polynomials in one variable with real coefficients if we treat x squared as being equal to -1 whenever it appears. This type of process of describing a ring as a factor ring of a polynomial ring, as I say, is something that appears throughout the algebra of commutative rings anyway, and is an essential component to the study of modern algebra.